In this video, we will be implementing a 3-wire SPI communication between two EK-RA6M4 channels. The Serial Peripheral Interface, or SPI, is a communication protocol where a master MCU will communicate with several peripheral or slave MCUs. The communication may be bidirectional but needs to be initiated by the master. To begin, we open the E-Square Studio. In a new workspace, we create a project called SPI_3W. As the device, we select the EK-RA6M4. We keep the default settings to flat project and executable build. For template, we select bare minimal. Once we click finish, the project will be set up. In our application, we start by setting up some data that needs to be sent over SPI. We then copy this data into the SPI write buffer and send it through the master channel. The slave channel receives the data and stores it. After that, we make some changes to the received data, such as adding a constant value. Then, we send the modified data back to the master channel and display it on the terminal. In the Renesas RA6M4 family, there are two modes of SPI operation: the 3-wire, which is also known as clock synchronous operation, and the 4-wire, which is also known as the SPI operation. For the 3-wire mode, the slave select line is not used. To develop the transmission process, we shall add the stacks for data transmission. We need to add two SPI stacks, one configured as a master and the other as slave. We can find the stack under connectivity. We name the master channel as G_SPI_master. Then we enable the interrupt priorities. We also rename the callback function to SPI_master_callback. The SPI mode is set to clock synchronous operation, which is the 3-wire mode. We also select full duplex for bidirectional data transfer. The bit rate is set to 9600. The pins are already pre-selected for the right SPI channel. We then add another SPI stack for the slave channel. We name it G_SPI_slave. We rename the callback function to SPI_slave_callback. The bit rate is changed to 9600 to match the other channel. The operating mode is set to slave. We then look into the pins associated with this transmission. We can make changes to the pins associated with each SPI channel. Since we do not need a slave select line, we can remove the pin assignment for the slave select. We do the same for the SPI1 slave channel as well. We then generate the project contents. For the connections, the master channel uses the pin 202 as MISO, pin 203 as MOSI, and pin 204 as clock. As for the slave, the pins 410, 411, and 412 are used. We will now open the hull entry file to start coding. The SPI call functions are already available under the developer's assistance. To print out on the terminal, we can make use of the Sagar library. The files can be downloaded from the Sagar RTT terminal website and need to be copied to our source folder. We will add an additional header file here, and we will include that in our source code. In the common utils file, we have all the macros related to the Sagar library. We will then define some constants to be used in our program. Then we will declare the SPI event flag variables. These flag variables are of custom data types and are defined in the FSP SPI library. We will declare the 8-bit unsigned integer arrays for the transmission and reception buffer. And we will also declare a variable to hold the length of our data transmission. Now, we will define the callback functions. We have defined the names of our callback functions in the stack properties. From the developer's assistance, we can already get the call definition for each SPI channel. In the callback functions, we shall store the appropriate flag events in the respective variables. Now, we move on to the main body of the program. We start by declaring and initializing the FSP error variable. The first step for SPI communication is to open the channels. We can call the SPI open function from the developer's assistance. We also add the assert macro, which ensures that the return status for the function calls are successful before proceeding to the next line of code. We initialize the input data as an 8-bit unsigned integer with a value of 0. We also specify the number of bytes to be transmitted to be a single byte. Then we create a while loop. In the while loop, we first copy the data to the transfer buffer and then print this input in the terminal. We then execute the SPI write function to dispatch this data from the transfer buffer. We also use the assert macro here. Then we change the arguments of the function to include the address of the source, which is the transmission buffer, length of transmission, the variable num bytes, and bit width, which is 8 bits. Then we insert the function call for reading data that has arrived to the slave channel. We store this data in the slave receive buffer. In this case as well, we specify the length of transmission and the bit width. We will then insert a while loop to check for the SPI event flags. These flags are set by the SPI callback functions once an SPI transmission or reception is completed. The while loop will exit once both the transmission and reception is completed and relevant flags are set. Once the while loop has exited, we will reset the flags. We will also print a confirmation to the terminal regarding the successful data transfer. Our next step is to modify this input. We conduct a simple addition to this value. Then we send this modified value back to the master channel. We implement the same procedure as before, only this time the slave is sending the data. We reset the SPI event flags after the transmission is completed, and then we print a confirmation on the terminal. We also print the output value, that is, the data that was received by the master buffer. We will then increase the initial value by 1 and add a 3-second delay, then end the while loop. The loop continues by sending a new value from master to slave. The program can now be built. Once build is completed without any errors, we can upload the program to our board. We need to find the address of the Segar block after the program has been compiled. This value is required to connect with the RTT terminal. Once we run the program, the output is displayed on the terminal. In each instance, the input is increased by 1, and the program adds 2 to this when received from master channel and sends back the updated value. And this completes a simple implementation of the 3-wire SPI communication on RA microcontrollers.